samples or in the contents of cells and subcellular compartments. He has guided more than 140 graduate students and numerous postdocs. Many of them have gone to build their own independent research groups. I'm happy to say that one of our own students, Mahima Sneha, did his PhD with him. For his outstanding scientific contributions, he has been recognized with numerous awards and honors and members in several scientific boards, advisory committees, and professional organizations. So the list is too long. I'm not going to list all of it. Let me just highlight a few. He has received the National Medal of Science from the National Science Foundation. He received the Wolf Prize in Chemistry from Wolf Foundation, Israel. The Priestley Medal from the ACS. The Welch Award in Chemistry from the Welch Foundation. National Academy of Sciences Award in Chemical Sciences by the National Academy of Sciences. He's also a member of several boards and is a fellow of many prestigious academies. And with this introduction, I invite Professor Zaid to deliver his lecture.
Thank you so much. I appreciate. Let me try now to share my screen. Just a moment. Here we go. And now I'm going to put this. I'm going to hide it so that I hopefully won't get in the way of what I'm doing. Okay, and of course, I want to thank very much my host, Raj, for inviting me to do this. And I have been to IIT Bhubaneswar before, and it's a pleasure to be with you, although unfortunately only remotely today. But let's begin. And let's see if I can make this go. Now, how do I get this to advance? Let's see. Here we go. So I want to speak to you on a new way to stop the spread of viral respiratory infections, something which I think is of great interest to us currently. Anybody who wants a copy of this lecture or wants to communicate with me, here is my email address. It's very easy to write me. I think you'll understand what I'm wearing as we go on very much. So let's begin. And I'm going to begin by talking to you about what causes obesity, which you may think have nothing to do initially at all with this talk. And as you know, obesity is a worldwide problem, particularly in my own country, in the United States. It's a very serious problem. And I'll talk about this because I think you'll see something related. Here was my mother's answer when I was growing up. She said, "You get fat when your intake of calories through food exceeds your output of calories by exercise." No one can argue with that statement, right? That certainly makes a lot of sense from a viewpoint of physics and science and so on. And her conclusions were twofold. One, do not overeat and count the calories you consume. So I grew up doing that. And indeed, she was very, and the whole family was very careful to say, oh, you should never eat avocados. Well, in Cleveland, Ohio, where I grew up, there weren't that many avocados. But since I've moved closer to Mexico and California, there's plenty of avocados. This is what her advice was because of the calorie content. And she said, engage in vigorous exercising every day. Exhausting. Okay, but still good for other reasons. And I'm telling you what, these two things, if followed, did not at all control my weight. And it turns out, in terms of what controls weight gain and loss, what you eat is more important than how hard you exercise. It's very hard to lose weight by exercise. Controlling metabolism by consuming the correct balance of foods, okay, is very important. This is the story of fats, sugars, insulin, and the keto diet. You need very much to be able to get insulin to control your metabolism. Today, there's been a great emphasis placed, at least where I live, on reducing fat in diets. And indeed, not only was there a worry about trans fats before clogging arteries, but as people removed fats, because fats dissolve spices, you remove taste. And to make up for this, people in the United States anyways, made their diet much more salty, much more sugary, sweeter and saltier. And the result has been an epidemic of not only diabetes, but of people getting fat. Something called the keto diet is amazing. I'm not recommending it necessarily, but I'm explaining to you. It actually works, and people do lose weight with it, though it seems to look like it's counter to the idea of calories. So it's very much a story evolving metabolism. And this is an example of how it's easy to get involved in sort of half understanding something and not realize the full value of what's going on. And we're going to see something similar that goes on, I believe, with viral respiratory diseases. So what controls the transmission of these diseases, such as influenza A or the what causes COVID, okay, our coronavirus pandemic? And there are two important facts. It's been hard to get these facts realized, but it's taken a while. But I think now people pretty much understand this. To begin with, it's transmitted primarily through the air. And it's okay. The transmission is from tiny droplets in the air, and it's not from coughing or sneezing alone, but it's from simply by speaking or singing. Singing is worse even than speaking. But anyways, putting out these droplets that contain virus from somebody who's sick. That's very much how it's transmitted. You're told all the time to go wash your hands. That goes back to historically to childbirth and what doctors learned long ago. It was important to stop women who gave birth from dying by washing hands, etc. But you can wash hands all you want. That has very little to do with stopping the coronavirus epidemic that we have. And so now here are the present strategies for reducing viral respiratory infections, at least that I know about. One, keep socially distant from other people. Okay, now how socially distant is still a matter of debate, and we can talk about that. Two, wear a mask, and that proves to be actually very effective. A lot of evidence shows that. And the three is clean the air in buildings. And people talk about cleaning the air three ways. They talk about primarily ventilation or filtering or UV irradiation. And we'll see that some of these can be overdone because they're leaving out another fact, which we'll get to. And I'm going to argue that this approach ignores another fact, namely the transmission of viral respiratory infections like the flu is seasonal and correlates with relative humidity in the air. Okay, relative humidity means how much water the air can hold, and we'll try to understand this. This is really not talked about much. It's recognized that there's a seasonal nature to this, but not really discussed. Let's look at this. Here's data from Paris, France. And I can show you data from all over the world, but this is, I thought, striking. This shows, notice, from 2012 to 2015. I see the scale, and these little things are the different months: January, February, March, April, May. And what do you see? I see that nothing much happens in the summertime, and I see big spikes happening in the wintertime. Okay, and the wintertime is shown in sort of this bluish gray. Sorry, this thing has come back. In the summertime in white. And this is true of influenza and of a bunch of other things, okay? And we're seeing the winter period and the summer period, and it's very clear. Well, okay, that's data from Paris, France. Here is a time series comparing FluNet data on seasonal influenza activity in the northern and southern hemispheres from 2015 to 2021. This was just published in 2022. Okay, so this is very recent. You find this in Nature Communications, and I've given you the reference. And what do you see? I see anti-correlation here because summertime and wintertime change between the northern and southern hemispheres, but it goes along everywhere the same. I tried to look for data in India, and that's hard to come by. So I'm not going to talk about that, though it seems to, again, show the same effect. And so I think at this point, you really should believe in the seasonality. Okay, why though the seasonality? What's happening? Truth is, little attention has been paid to seasonal variation of viral respiratory infections. Indeed, here's a remark that I thought quite arresting. It's from this person, Scott Dowell, who works for the Bill and Melinda Gates Foundation. And Scott Zimmerman brought this to my attention. I appreciate that, Scott. And I'm going to read it to you. If we knew what suppressed influenza to summertime levels, that would be a lot more effective than any of the flu vaccines we have, unquote. Wow. Okay, that's interesting. So we want to think about this. And so what varies with season? And there's many things that vary. One of them is the temperature. We'll talk about relative humidity of the air. Another one is human activity. Okay. And we'll try to see what happens with this. I think I better start with the temperature first of all. Turns out the virus is very happy over a large range of temperatures, unless you get so hot that you actually denature the system. It's fine if it's hot, and it's fine if it's cold. So it isn't simply the temperature alone, but it is, it turns out, indirectly. And I need to explain why. Here's some lovely data from Dr. Stephanie Taylor, a person who's an MD who's also an architect. And she says, what's going on? Humans have become, she calls it, Homo indorus. And what that means is if you look back a long time ago, people lived and worked 100% outdoors. They lived in tents, okay? Everybody was outdoors. Then humans lived in buildings, still spending 100% of life outdoors, as I mentioned to you. 200 years ago, working in factories and offices, living 90% indoors. In fact, today, 90% indoors is what's going on. The industrial evolution, okay? Work is in centrally heated and ventilated buildings. In the last 20 years, we live and work in airtight, mechanically ventilated buildings in a large part of the world, okay? And so you see, we really moved there. So it's a lot of it is indoors. It's indoors in the summertime, indoors in the wintertime. 90% of our time is spent indoors, okay? So how can outside temperature influence seasonal variation of sickness? And I wanted to show you something quite interesting. This is data now from Gothenburg, Sweden that I have, but I have other data too that's like this. Let's look at this. Here is indoor relative humidity in percent. And it goes up a little over 50% and it falls to a little below 30%. Okay. And here in red is the temperature. And after all, it's Sweden, so it goes below 0 degrees centigrade, as you see, in the wintertime. Okay, and we got it, and it gets not much higher than about 20 centigrade in the summertime. And the difference between 30% and 50% relative humidity strongly correlates with respiratory illness. This is a fact. There's lots of correlations. Some matter, some don't matter. Why is this matter at all? Not yet obvious. Let's look at some more data. Here is some data that's published. Let's see, when was this published? Okay, oh man, I'm having trouble reading this. Okay, here we go, 2021. So I'm showing you very recent data. Here's the sum of weekly new confirmed COVID-19 cases per 1 million people across the 5 representative countries that this group looked at: Canada, Germany, India, Ethiopia, and Chile, for the period of March 2020 to March 2021 as a function of weekly specific humidity. And it's very clear that as the total confirmed cases really vary such that if the specific humidity is low, they go up. And if they're high, there's also some going up, but in between, there seems to be, look at this sort of U-shaped. There's a sweet spot somewhere here. And so we're trying to understand this. And I'm just showing you some data that really indicates this. We'll see more like this. And here's yet more data trying to convince you what I'm telling you. Here's indoor relative humidity, that's in blue. And here's New York, oh, come on back, come on. This is New York City flu cases. And we are seeing that when the relative humidity goes way down, the flu cases go up. And this is, of course, again, a span over years. And it's not only true in New York, it's true in Texas, okay? And it's the same behavior. It's also, we see this in some studies that have been done, again, by Stephanie Taylor in hospitals about respiratory and GI infections rates were lowest when the indoor relative humidity is somewhere between 40 and 60%. That's what you really want, and it's very clear from that. Yet more data showing this type of effect. And I think this one's in specific humidity, and you're seeing how when it goes up, how the disease rate goes down. And these are influenza cases in this case. Okay, yet more. I hope you're getting a sense now. Very that data that's here. This one again shows you what happens in, I think it's Buenos Aires in Argentina. Okay, and it shows you daily relative humidity, and when it really falls down, look, about 9 days later, there's an induction period. Look at the rise of the cases of COVID. Okay, and we see what that's like. Okay, whoa, what's happening here? Low ambient humidity impairs barrier function and innate resistance against influenza infection. This is a study made primarily, I think it's at Yale. Yes, at Yale University by these people. And they show that using a genetically engineered mouse in low relative humidity makes mice more susceptible to severe disease following respiratory challenge with influenza A virus. And they find that the inhalation of dry air impairs the mucus clearance, okay? And single cell RNA sequencing reveals the induction of this so-called stimulated genes in response to viral infections was diminished in multiple cell types in the lung of mice housed in low humidity condition. So lots of things are happening that way. You really want to control the humidity if you can. Let's learn more. Here's infectious droplets and how they travel. As they travel, they shrink, they evaporate, and they travel far when the air is dry. Let's understand that the virus is very happy in water. Water doesn't bother the virus at all, okay? If you remove all the water, the virus is desiccated, but it's dormant, but it's still active. And as it gets smaller, it hangs around. This gives you the float time, 41 hours to 21 days when it gets to be really small. Whereas if it's large, this is the distance in microns, okay? It really falls to the ground, basically. Doesn't go so far. And so now relative humidity and the survival of microorganisms in water droplets. This has been studied, and again, I'm just trying to remind you, this is what a bacterium looks like. I think you're familiar with it, with a coating, et cetera, around it. And here's, of course, our virus and of a nucleic acid and a protein coat like so. And here's what Lindsay Marr found at Virginia Tech with Case and Lynn. And she found, if you look at virus viability, and this is relative humidity, there's again a sweet spot. The viruses are killed in between, but if you make it too low or too high, they're not, okay? And so something is happening in between. Now, that's not true of bacteria. Bacteria really are acting a different way. So this is the bacterial viability. And as you really make it down, they are killed, okay? They really do kill bacteria if you get the relative humidity down, but not viruses. Let's see what she says about this. Here's the findings of the study. Survival of bacteria increases as relative humidity values increase. It is thought that increasing evaporation increases salt concentration. Remember, it's from us, from saliva, and we're all salty. And it's thought that the salt will actually kill the virus, and it'll do that by changing the osmotic pressure and bursting the bacteria. It'll kill bacteria that way, okay? Survival of viruses has a U-shaped curve, doing better at higher and lower relative humidity, but worse at intermediate RH values. That's what she's found, and I'm showing you plenty of data supports this. She writes, this is, very recent data, very recent comment. The mechanism underlying the relationship has not been explained, particularly for viruses. Okay, of course, why I'm talking to you is I want to offer to you a possible explanation. Let's again look at some more data. Let's see if we can find out when this was published. This was published 2021. I'm not a person who reads building and environment, so it's very hard to come across this stuff. And this is indoor humidity of dwellings and association with building characteristics, behaviors, and health in northern climate. And so these are people who primarily seem to be in Scandinavia, in Sweden and Denmark, that are writing this. And here's what they find. Analysis shows that low indoor relative humidity is a realistic issue in Swedish dwellings during the heating season. Well, you understand why. We heat the air to keep ourselves warm and we dry it out. I hope I've made that clear to you. The issue is more prevalent in apartments than single-family houses. In addition, low indoor relative humidity seems to be more extensive in dwellings with higher indoor temperature, smaller volume, higher ventilation rates, and frequent airing practices, lower number of occupants constructed mainly after 85, because they seal them, they're real tight in city suburbs and in the northern parts of the country. This analysis offers additional evidence to the scientific literature for possible correlation of low relative humidity with specific health symptoms, complaints, and disturbances. Okay, we're seeing that. What else? Here's another study. This study is published when? Oh, okay. This one is so recent that it hasn't even been, it's only now online. And it's environmental risk factors of airborne viral transmission, humidity, influenza, and COVID in the Netherlands by these people. And what do they find? They find an inverse negative relationship is observed between specific humidity and the incidence of influenza between 2015 and 2019. The space-time analysis indicates that an increase of specific humidity of 1 gram of water vapor per kilogram of air is related to a reduction of approximately 5% in the risk of COVID. Okay, so we're seeing all this. Their conclusions are the following. The increase in humidity during the outbreak in the Netherlands may have helped to reduce the risk of regional COVID. Policies that lead to an increase in household specific humidity to over 6 grams per kilogram will help reduce the spread of respiratory viruses such as influenza and SARS-CoV-2. And how do you increase the humidity? Well, there's a device called the humidifier, basically. And I think everybody understands that. You evaporate water. Okay. And so how long the coronavirus survives in air depends on relative humidity. And so here is more data. This is now July 7th, 2022. That's not so long ago, okay? These people have written the following. For example, at low relative humidity, below 50%, the particles undergo a phase change. They crystallize as water evaporates off the aerosols and salts within them concentrate. All that's explained. This is Jonathan Reed. This was published in the in PNAS, Proceedings of the National Academy of Science in the US. He thinks it's all due to salt, but we've seen that doesn't work for viruses. It works for bacteria. At higher humidities, another slower mechanism dominates. When relative humidity approaches 90%, a big driver for the loss of infectivity is actually a very rapid pH rise. So he thinks it's pH related. Okay. As a result, in more humid air, infectivity drops by 50% within the first 5 minutes and then decreases by 90% within 20 minutes. Okay, I think the data is great. I think the explanation personally is not convincing. I want to offer a different possible mechanism that can explain the behavior for viruses. Okay, let's begin. Here's the first claim. Water microdroplets contain what I'm calling reactive oxygen species, or ROS. And it's unlike bulk water. I often refer to this as water droplets as being made of aqua ROS, okay? So I'm telling you, it contains reactive oxygen species. And I want to show you that and hopefully prove it to you so you really believe it. I want visual proof of the fact that hydrogen peroxide, that's one of the reactive species. Incidentally, much more reactive is OH, which makes up H2O2, as we'll get to. So we need a probe. Here are some probes developed at Berkeley by these people. Look, this thing has a boron carbon bond, but the hydrogen peroxide snips this off, and you're left with this molecule, which some of you will recognize as fluorescein. That's fluorescent. This thing has a name. We're going to call it PF1. The IUPAC name's hopeless. Okay. Good. PF1 is non-fluorescent. Let's now look at this. I'm going to dissolve make a 10 micromolar solution of PF1 in bulk water. And I'm going to show you a bright field image of the bulk water. Here's even the water in a beaker with the air above it. Okay. And I want to now show you the fluorescence, and you see nothing. At least I see nothing. Okay. But what happens if we instead make droplets? And here are droplets. And in fact, if anything, as the droplets get smaller, they get brighter. And you're seeing the bright field. Can you see the droplets? I hope you can. And you see the fluorescence very clearly. This fluorescence is coming from some reactive oxygen species from hydrogen peroxide. Okay. And so now we want to get really good further to understanding the dependence on droplet size. And here's what I'm telling you, non-fluorescent to fluorescent. Same stuff, okay? And here we go. We're going to use a confocal microscope, and we're going to scan along droplets. And here is work. J.Q. Lee primarily led this study, and he's now at Seoul National University in Korea. And I wanted to show you the beautiful work you see. Look, here is the bright field. Here's the fluorescence. Here again is the air, water, and you don't see anything. The fluorescence imaging of spontaneous generation of hydrogen peroxide in aqueous microdroplets. We get a sense of what's happening to this. And the scale bar is about 20 microns. So when they get smaller than 20 microns, they really glow. And that's shown really here. Let's spend just a little bit of time on this because this will help. Here is water droplets in air, okay? And I'm trying to show you, there's the bright field. There are 3 droplets, A, B, and C. What's their size? Well, I'm showing you down here. The A is 160 microns. To help everybody imagine, the thickness of a human hair is generally about 100 microns, okay? B is 50 microns, and C is 16 microns. And look, C really lights up. B, there's a Vegas hint. And if you really have sharp eyes, there's just a little bit in A, but hardly any. And that's shown you in this graph. So the smaller droplets take off, okay? Fluorescence intensity versus microdroplet diameter for 1 to 50 microns. Okay, we get this. And now I want to, if I can, here's more data that we've taken. This was actually Catherine Walker who first suggested this. Let's start, my student, let's start by playing this. What are we going to see? This is going to be a video. I hope it'll play. And here is a test strip. This is paper that has on it an enzyme, horseradish peroxidase, and some dye. And if this contains, if you just touches water, nothing happens. But if it contains hydrogen peroxide, this will turn blue. Okay, so let's now play it. And if you look carefully, hopefully this is playing, this is getting wet over here. Okay, this is our sprayer. There's no electric field at all. This is just air or nitrogen forcing out water. Here's the little capillary. Now we're going to line it up, and it's now spraying on this stuff. And patience here, this is being played times 10, and you watch, it's turning blue, I claim. Okay. And yeah, it's getting to me pretty visible that it's blue. And so there's hydrogen peroxide being formed. Well, people have said to me, oh, Dick, that's because you somehow are charging up your droplets because they're moving and they're rubbing against some surface. Actually, that's not the explanation. But to show you that it's not as simple as that, I want to show you the next video. Here we have a device called a Peltier cooler that makes things really get cold. And we're going to place on this. Now this is work of 2020. And let's show it. We're going to place on this a silicon disc. Here we go, Peltier cooler. Here comes our disc because it's nice and reflective. And when it's cold, it's just going to take the water out of the air. It's going to make droplets of water, and you can start to see them condensing. See over here? Okay. And this is proceeding. And now we're going to go ×5 because otherwise it's like watching paint dry. So this is 5 times faster than what really happens. And you can see the droplets being formed, I hope. Very, very clearly we have droplets. I hope everybody sees that. Now here we go with our test strip again. And water, this doesn't change color at all. Now put this on this and watch. Any doubt? I hope not. Okay, we really see what's happening here. Let's move on. So here's my next claim. Hydrogen peroxide comes from the recombination of hydroxyl radicals in water microdroplets. Now, if you ask somebody, what does water contain? And particularly if they're starting chemistry, they tell you, oh, it's H2O. And you say, well, suppose you have a 1 beaker filled with water, a beaker with 1 liter, 1 liter beaker filled with water. You have 1 liter. What does it contain? And the person says, oh, I know that it's 55 moles of water, right? You smile and you're happy. Now you say, well, does it contain anything else? And the person looks at you and says, well, yes, actually, there's 10 to the minus 7 moles of H plus and 10 to the minus 7 moles of OH minus. That's, after all, water's neutral. And that's why everybody who starts chemistry learns that the pH, which is the negative logarithm to the base 10 of the H plus concentration, is pH of 7, okay? Fine. And so there's OH minus, that's the hydroxide, but I'm interested now in OH. Somehow we're going from OH minus to OH. And the question is, do we have any evidence for hydroxyl radicals in water microdroplets? Let me show you. And here we are. And this is showing you, if you add this particular scavenger salicylic acid, that you can form these compounds. And I'm showing you in a mass spectrometer that indeed we see them. We were able to trap the OH. We know that there's OH being formed in water droplets, not in water droplets. Okay. And here's yet another study. This one was just published in 2022. Okay. It very much, Xinxin Chang and his group are responsible for this study. And we're spraying water and we're looking and we're seeing here a peak at 36, which corresponds to H4O2 plus, which is really the OH dot captured by H3O plus and showing up. And we see it, it's there in droplets. So when you spray it, you got this. And this is a reactive species, and that's held together, and that's a very potent ROS, reactive oxygen species. Okay. Now, it's been questioned whether H2O2 can be produced by water droplets acting alone. We said yes, but it's been suggested that it comes from ozone being absorbed by water droplets, and that's this work headed by Mishra from Kaust in Saudi Arabia. Okay, and indeed, there's no question that ozone can make the thing turn into hydrogen peroxide. Okay, that's so. But if you look way down here, this is not as clear. And we have recently published a study. This is, again, notice how recent this stuff is. Okay, this is now in JACS, the Journal of the American Chemical Society. And we have looked at that water microdroplets are able to generate hydrogen peroxide by themselves. How did we do this? Well, we actually bubbled these gases through water to try to absorb anything that take away that they had. Then we went on, we put them through an ozone scrubber. We sent them into a chamber. This is the water-filled capillary with a pump that goes through. And then we're able to collect the stuff and actually run NMR on it, okay? And keep it sealed and do that. We also have an ozone monitor. We know there's no ozone. This is a quick setup of this quick picture of our setup. And what do we see? And so here's an NMR spectra. The black is 5 micromolar hydrogen peroxide. That's a standard. And the red is what we found. And it's on the order of about 1 micromolar or so, micromolar hydrogen peroxide that we see. It depends on the concentration. The H2O2 concentration depends as a function of flow. This is now ultra pure nitrogen. It is 99.999 pure nitrogen, and we've done everything we can to remove oxygen. Indeed, we find that O2 can help this happen. So O2 on water will go on to make O2 minus, take an electron off of the OH minus on droplets. But and this is, you see as you do this, but just in pure nitrogen, it's still there, okay? And now this is this to me is some really most convincing work. Bolai Chen and co-workers have done this gorgeous study that's just come out again in PNAS. And here is a material which is non-fluorescent, which becomes orange fluorescent in hydrogen peroxide. And here is water next to glass. Okay, that's just a picture of bright field. Here's the fluorescence image. Please notice it's orange and darker right by the glass and diffuses away. And that's shown here as this graph. This is the intensity. And so and there is no gas getting into here, okay, particularly. So please just forget about gas at the moment. Gas can make this happen, but it can happen by itself. And it's obviously happening by a glass-water interaction, touching each other. And so, and we're gonna go on and tell you that this comes from what's called contact electrification. And I urge you to take a look at this paper if you want to learn more. It really is happening that species will lose their electron to the surface. Many things can happen. H2O dimer in water can itself go on to form H2O plus, H2O minus, and the electrons can come off to this on contact. And the next claim I want to make to you and hopefully convince you about is that aquaros, what I'm calling this, acts as a disinfectant. This is work that was done primarily by Maria Dulé and my research group, and published as showing you that it's a bactericide now in 2020. And here's Maria and other people who joined this project. We've had help from a lot of people and been inspired by these people who really pointed out to us, Adrian Davidsa and Sanisa Vukovic, the importance of this potentially with regard to viral transmission. These two people are in immunology and helped us very much so we could count and learn about cells, because that normally chemists don't learn about that too much. Okay. And here is our technology. Very simple again, nebulizing gas and water. Please notice there is no electricity being applied, no voltage, no current. Okay, this is just being sprayed on something beneath it. So the advantages are that this is non-toxic. Okay. Okay, and what do we find? Let's see if I can go back. It uses ordinary water indeed, we've come on back. We've played with salt water, that works too. It's inexpensive, it's simple and easy to apply. And we find direct destruction and inhibition of pathogens on various surfaces. And we think it will be used in food processing. And I want to show you how well it works. It kills like 99% of E. coli and salmonella. Okay, we've tried it even on spinach, etc. And we see this work, and we can actually in like 1 minute kill like 96%. If bacteria are sit on top of other bacteria and hide, instantly, we've done this with viruses like tobacco mosaic. It also works. Same thing. How does it work? Well, your ROS, your reactive oxygen species, punch holes in things. It's very reactive. And I'm actually showing you pictures of that, of what we see is going on. So you hopefully will believe this is really an effective disinfectant. Okay. Now, claim 4. The H2O2 production in water microdroplets sprayed in air depends on relative humidity of the air in terms of the OH. I want to really show you this. Now, this came about to us actually, in some sense, not because we looked for it, but we found as we would keep running these experiments, they were varying from day to day, and we finally traced it out. So here's a publication. Again, this publication is relatively recent. I don't remember quite when, 2021, okay? And it's the effect of relative humidity on hydrogen peroxide production in water droplets, okay? And here we go. And what do you see? I see that the relative humidity, this is relative humidity here, when it's 23%, we're getting 2 milligrams per liter. When it's 53%, we're up to over 6 milligrams per liter. And here are all the conditions. We're getting a factor of 3 increase. Okay, so first of all, relative humidity, the right amount, really helps the droplets that hang around and have enough time and causes these H2O2 to go up. And I now want to try to get you to understand the universality of H2O2 spontaneous generation at water solid interface. And I find this data remarkable and very important. I'm showing you what happens with various particles. This is the intensity, okay? This is the intensity of H2O2 production. And this is on graphite, calcium, lime, okay? Various things. These are different particles. And here's the relative humidity. I'm showing you as the relative humidity goes up, this also makes it go up very clearly. This is the H2O2 concentration in, this is on what's called PM 2.5. What is that? Particulate matter 2.5. Lovely work done again by Bolai Chen and co-workers in China. And this is their data on this. This is the dependence of H2O2 generation on different water solid interfaces, H2O generation on a standard soil surface with various surface treatments under different relative humidities, and C is that generated under different relative humidities. And I hope you're catching on to all this. Okay, so let's now see what some people are saying and see how this fits. So now I hope you believe that droplets are going to have lots of hydrogen peroxide or reactive oxygen species. Much more important probably is OH. But to continue are other things that may be happening. Not clear yet what chlorine might do and whether or not you can get such things as bleach from it. This study examines the structure and evaporation dynamics of virus-containing saliva droplets. When was this published? Okay, this one is, when was it published? I think it's still only as a thing that you can get online. Anyways, they've looked at the Newcastle disease virus and coronavirus, and the results support the hypothesis that the direct contact of antiviral proteins and virions within what they call the coffee ring region of the droplet residue gives rise to the observed U-shaped relationship between virus viability and RH. They say viruses survive much better at low and high RH, and their viability is substantially reduced in intermediate RH. And I'm showing you there's other reasons for this. Now, what do they mean by coffee ring? Let me show you right here. It's this edge stuff. Notice there's salt being formed down here. Salt is not what kills virus, okay? And this is where it is. And we've seen that this contact is very much, that I've mentioned to you, can be where you generate reactive oxygen species. Here's another study. When has this study been published? Let's see. This one is back from 2012. This one's very interesting to me. This is the generation of reactive oxygen species in water under exposure to visible or infrared radiation at absorption bands of molecular oxygen. This is actually work done in the Russian Federation, okay? And look what you see. You see sunny, you see cloudy, and you see, oh, come on back. You see no radiation. And it's clear that sunshine, okay, really is helpful in making this stuff. So we're learning yet another fact that I'm very grateful to Scott Zimmerman for pointing out to me. The kinetics of H2O2 formation in by-distilled water upon the action of sunlight, mean water temperature, 5 to 9 degrees centigrade, subjected to the action of sunlight, shown in the, different illumination conditions. This is the control samples without the action of light. Very important. Wow, it's really getting interesting. The more we can get back to nature, the more we can get outside where there's good relative humidity and where there's a lot of sunlight, the more healthier we'll tend to be. Okay, so now we're going to talk about public health implications. I hope you're starting to see this. There's been such emphasis placed on just ventilation. And I'm for ventilation, but I'm telling you, you can overventilate. And I've talked to people who do architecture, and I've asked them, why don't you increase the relative humidity in buildings? And they say, in the wintertime, it's no good because you see, you get droplets of water on the windows and people don't like that. So you don't want to have that. So and of course, windows are not double paned, or you get around that problem. If they were, you have no such problem. And I want very much to have you think about this. So give you an example now of where this matters. I've shown you how things vary with relative humidity. I bet a lot of you have taken airplane rides. Airplanes are one of the worst places you can be in terms of getting a viral disease. Everyone knows that, actually, that it's very easy on an airplane to pick up some type of respiratory illness. What's the relative humidity in an airplane? Well, around 5%, awful. Okay, what is the lighting of an airplane? You're in the dark. Okay, both of those, losers. And there are simple fixes to this, but the airline industry brags to you about how many times they change the air in the airline. It's no good. Let me say it again. Someone's sick on the airplane. They just speak. They don't have to cough or sneeze. Out comes droplets that contain the virus. Okay, with such low relative humidity, okay, it rapidly evaporates. And now it floats around, and as I've shown you, it can last a very long time. And someone else gets sick, and we sort of see why. If it can be the right relative humidity, it stays as a droplet with the right size long enough for the effects of electric field and this contact electrification to really cause the OH minus to go to OH and to have all types of reactive oxygen species that can kill things. Very important. So I hope I'm giving you a picture. So I want to now, if I can, reach some conclusions in this talk, and let's do them. Here are my conclusions. First, the variation of reactive oxygen species, that's ROS, with the percentage relative humidity of the air helps to explain why 40 to 60% relative humidity is most healthy and why there's been a seasonal variation in the transmission of viral respiratory diseases. Because people have not wondered that much before what's causing the seasonal variation, they haven't caught on to its importance. It's just considered, a fact. We need to change the paradigm from cleaning the air to reducing the load of live viruses in the air. And this is an important idea that I'm mentioning to you, and we can indeed do this. And how do we do this? So this change calls for a new strategy that pays attention to include proper lighting. We've seen that can be important too, and setting the proper percentage RH for the indoor air in buildings, as well as cleaning the air. I hope this gives you some idea of why I think this area is so important to us, and also hopefully shows you why I very much love microdroplets and so much more to be done with it. So I think at this point, I'd like to stop and if possible, let people make comments and take any questions. So thank you again. Let me now stop the share of the screen. Okay. If someone else, I'm so pleased to see you, Jay Mittal.
I am listening. I am very
Thank
much
you for
here,
joining.
and I'm getting very much worried because we live in Mumbai where the 90%, 95% humidity in the entire July to September. So what will happen to us? Bad
I
news.
understand. But of course, it's not 95% in your home.
Hopefully
But it is
not.
high.
Windows are open
Yeah.
and there's not enough light because all the time cloudy.
Right. If I might, Scott, can I call on you to say something? Are you still with us?
Yeah, I'm here. No, I think that I really appreciate the talk. I think you addressed the issues. You know, our work has been mainly associated doing the optical side of things, and you know, what we did is we basically looked at taking in when your light shines on the body, it generates a certain amount of reactive oxygen species, including hydrogen peroxide. But then we've also started to extend that into looking at the optics of a droplet. And just as you've shown with the amazing things that happen on a chemical standpoint, it's amazing how optically droplets are much different than just bulk material as far as what wavelengths are absorbed. So that's
I
been
want to
our
actually
focus.
comment on something with regard to droplets that people understand, but they don't think about. Please, droplets cause rainbows. Okay,
Yes.
we know that from rain, we know that, we see it in the
Yes.
sky. What's happening? All the light that goes into the droplet is concentrated on the backside of the droplet because of the refractive index of water. And the result is that you really increase the intensity at the backside of the droplet. And it's the water-air interfaces where all the action is, and that I've been mentioning to you. So there's real reasons to think about droplets again. Professor
Yeah, well,
June,
if you actually do the optical models of a droplet, it's amazing as a function of free wavelength. You know, water has very low absorption in certain parts of the spectrum, but very high absorption in other parts. And what's amazing is that we have literally removed the portions of the sunlight that actually get absorbed by droplets in our homes with visible only lighting. We took out the UV and the near infrared and this shortwave infrared. So we've got a lot to learn, I guess.
well, we have some changes to be made, but getting people to pay attention to this has been very hard, for at least I've found. First of all, I regret, I've tried hard to interest the press because the public needs to know this, and that's not at all succeeded. I've gotten no public coverage of this yet, and this frustrates me because it's only by people starting to understand this that we can start to really make changes. All the building codes are still busy talking about ventilation and not about anything doing with lighting, not anything to do with relative humidity, just left out.
Well, you know, in a lot of ways, the basic tenet of most disinfection theory, or whatever you want to call it, is based on the assumption that that nature does nothing and the body does nothing. It's we're going to kill something we're going to introduce something to kill it versus
Right.
it doesn't understand. We don't understand that the nature and body are fighting a battle continuously against unbelievable odds. I mean, I think they argue that there's 10 to the 33 virus at any given time floating around and pathogens. You know, the body's been fighting this battle for millions of years, and it's not totally, you know, helpless.
Then I'll say something else, which will sound like heresy. There's actually good viruses too. Okay.
Yes.
You don't want to kill all virus, despite what people tell you.
Yeah.
Okay?
Yeah.
Yeah.
And very complicated things. Plus the fact that, again, some lovely studies that you've told me about, in which just having ourselves exposed to sunlight produces inside ourselves reactive oxygen species. And I'm telling you, ROS is a key to understanding some of our defense.
Well, I think that what you're going to see more and more is the medical community is starting to understand that there's a basal level of ROS that's generated in the body and that it does something. It's part of our innate immune system. And when we move inside and don't get the exposure, a lot of that is driven. You get up to 30 megajoules of energy deposited into the body every day just from sunlight. And now we go inside and we get a fraction of that.
Okay,
and
so
it changes
please
the
don't
entire
sit
chemistry of
in
the
the
body.
dark on airplanes. It's a bad thing to do.
Open the windows.
Yeah, I just think it's a seasonality and how nature can totally eradicate a virus, basically, or stop the flu for hundreds of years, is something that we need to dig deeper into.
Someone else want to comment, please?
Dick, it was an extremely interesting lecture, and given in the usual fashion of Dick's style, it's very, very good. But now I just have one small technical question: that how do you recommend the control of the micron size of particles? Because you have shown very clearly this 1 to 50 is the critical.
It turns out you can easily make a spray. A perfume bottle will do it. Honestly, you can easily make sprays with very small droplets.
Mm-hmm. But control.
And anybody, these are like fog generators or mist generators. You can do it. So that we technically know how.
Mm-hmm.
Okay, Dick, I think the audience here might have some questions. Can we take some?
Please.
Okay, yeah.
So good evening, sir. My question is, you showed us some materials, for example, SiO2, Al2O3, and ZNO. So what is common in these materials which help the production of H2O2? So what is there in these materials? Is there any relation?
I'm still trying to understand all that. Something that's very common is to have oxides on the surface. That's one part. But it looks like when you put two phases in contact with each other, you really can easily get charge transfer to happen. We've known this for a long time. That's a so-called contact electrification. And here I'm very much influenced by the beautiful work of Chonglin Wang, who's both at Georgia Tech and I think now in Beijing somewhere. Okay, who's done so much beautiful work on this. This is so, and we're seeing this. And so it's very common when we have different phases, water talking to other phases, we get charge transfer. And that's what I'm trying to show you.
Okay, so I have one more question. Could you please explain this coffee ring region once more clearly?
I think it is the place where you have air, water, and a surface all in contact with each other. Is at the ring, at the outside ring. Agreed? And
Okay,
I was showing you, for example, that oxygen on water, I don't think I've explained totally. There is a huge electric field set up at the interface. When I say huge, how huge is huge? Okay. We've actually measured, this is now beautiful work of Wei Min's group at Columbia University that we've gotten involved in. And it is on the order of, I'm trying to remember, something like 10 to the 9th volts per meter. Okay. Okay, so that's huge. I can't make fields like that in the lab without getting lightning, but we're having these at interfaces. And this really helps OH minus lose its electron to form OH, or even H2O plus H2O minus to have its electron come off. Okay, all this is so. So there's a very interesting interplay of physics and chemistry, which we now notice has very strong biology interactions in it. It is a highly interdisciplinary area. Okay. And I don't fully understand all of it either. I don't want you to say, oh, it's now all solved. Not at all. Please, there's much more to be done here. But there's all types of possibilities. I'm actually further excited in the ideas of how this can actually allow chemical synthesis to happen. Because once I have OH species, I can start to do all types of chemistry. We've seen some of that.
But now Air Force people and the airlines people must be very much worried, because there will be all interactions with the metal and aqueous and water.
Well, I forgot to acknowledge that all our support for this work has been coming from the Air Force.
Yes.
And may it continue.
No, I wonder.
Though the Air Force is not so concerned about coronavirus, but they are very interested in know what's going on in the atmosphere and in aerosol particles. And we're really showing you this is so.
Oh, corrosion is a very big problem there.
Right.
And it also is a problem in our industry, atomic energy, in the nuclear reactor inside. It's full of water, and there's a lot of water vapors, and there's a lot of metal surfaces.
Yeah. And I'm showing you it is the contact between the water and the outside containers where the action is. It's at the interface.
Hello, sir. My question is, like, when you do these studies in nature outside, how do you measure these properties or H2O concentrations, unlike in lab where you can make the droplets? If you have to do these studies outside, what techniques do you use?
Well, you collect the rainwater or aerosols or any of these particles, and then you have a whole bunch of choices. You can do NMR and add backs at NIH has really showed us how you can do NMR and detect H2O2, and you'll see that in our publication. Or you can add some compound which becomes fluorescent, and then you can do fluorescent studies, or you can do colorimetric studies, as you saw with the test strip that I have. And there's various titrations we've done. So there's a whole number of different ways of detecting hydrogen peroxide, or if we're looking for OH.
But how do you measure the size of the droplets that are
Oh,
formed?
by light scattering. There are devices that are already being sold, and we actually bought one which does diffraction and allows us to see the size of the droplet, also under a microscope.
Okay, thank you, sir.
I mean, okay. We're not talking about nanometers. I'm talking about microns. Okay, so that can be seen.
I have one question.
Please.
First, thank you for your beautiful talk. I wonder about the impurity effect in microdroplet. There are so many impurities in ambient air, such as dust and carbon dioxide.
Right, I think carbon dioxide is a very important matter, and dust, both of those, because I've shown you that those again, like on dust, I've shown you all the dusts lead to hydrogen peroxide generation. So very important. And we all talk about pure water, but please, somebody show me pure water. It's very hard. Water is such a good solvent. It's very hard to make pure water, and to keep it pure.
Well, to keep it pure is even more difficult.
Yes, you burn hydrogen and oxygen. I agree. You can start with water, but oh wow, you got to contain it in something.
Thank you so much.
Mahima, what a pleasure to see you.
Hi, Dick. How are you doing? It's very
Are
interesting.
you in Germany right now, or where are you now?
Yes, I'm in Germany at my home and I have COVID.
Oh, no. Oh, I'm so sorry. I've had that too.
No, yeah, I know. You told me about it. It's very interesting because, I went to Italy and I thought it was super humid. And I was like, oh, is it somehow correlated with humidity? But it was very hot and very humid. And you talk about this U-shaped curve. But we talked about having higher relative humidity where it is responsible for killing the viruses. But then there is this range, the U-shaped curve, right? You never talk about the very, very high humidity, like what's happening at that 90, 80% relative humidity.
The virus is very happy because your droplets are large and they also don't spend enough time in the region where they get killed, the right
Good.
size.
So
Okay.
so and what about with respect to the reactive oxygen species? Is it like getting too diluted at that point, or
It also gets diluted because it's only happens, it's a matter of the surface area to the volume of a droplet, and you do better is you make the droplet smaller.
I see.
This way, 4 pi r squared versus 4/3 pi r cubed, et cetera. We call that out. Okay. And take care of yourself now.
Thank you. Yeah, no, great talk. Really enjoyed it.
So anybody who wants, again, more information, a copy of this talk, just email me, and I've given you my email address, and I'm also happy to send you this presentation.
Okay, thank you, Professor Zare. It was a great presentation and we enjoyed it all. This is Devasmita, and on behalf of entire NICER, we thank you all. Thank you for a very nice presentation. It was very informative, and I'm sure our students will have more questions and they will actually come and talk to you or write back to you. Thank you once again from all the team and the students sitting over here.
Thank you all. Thank you for having me. I appreciate it. So
Thank
I
you.
think I say goodbye now.
Thank you.
Nice
Thank
to
you,
see
Dick. See you again.
Time for my breakfast.
My dinner.
I think.
Bye-bye.
Bye.